Hey everyone, welcome back to Instrumentation Lectures. In this video, we will start our discussions on performance characteristics of measurement systems. This lecture is lengthier than usual, but I assure you that we will be covering everything there is to learn on the topic and every concept will be clear by the end of the lecture. Let's start our lecture now. Before going to discuss instrument performance characteristics, it is desirable to learn about a generalized input-output configuration for measuring instruments and instrument systems. Here is a figure showing the configuration. The input quantities to any instrument system are classified into three categories: desired input, interfering inputs, and modifying inputs. Desired inputs represent the quantities that the instrument is specifically intended to measure. It produces a component of output according to an input-output relation symbolized by Fd, where Fd denotes the mathematical operations necessary to obtain the output from the input. Depending on the particular input-output characteristic that is being measured, the symbol Fd may represent different concepts. For example, for a linear system with a constant static output for a constant static input, Fd might be a constant k. On the other hand, Fd may be an algebraic function like f of x in the case of nonlinear systems. Next, we have the interfering inputs. Interfering inputs represent quantities to which the instrument is unintentionally sensitive. The symbol Fi serves a similar function as that of Fd for an interfering input. The third classification of input is modifying input. Modifying inputs are those quantities that cause a change in the input-output relations for the desired and interfering inputs. That is, they cause a change in either Fd or Fi or both Fd and Fi. The symbols Fmi and Fmd represent the specific manner in which the modifying input Im affects Fi and Fd. Now the output of the instrument is the instantaneous algebraic sum of its two inputs. Okay, let's take an example to make this concept more clear. Consider the mercury manometer used for differential pressure measurement. The desired inputs are the pressures P1 and P2, whose difference causes the output displacement X, which can be read off the calibrated scale. Now, these two figures shows two scenarios where interfering inputs are present. In this case, the manometer is mounted on some vehicle that is accelerating. By our experience, we know that there will be an output X even though the differential pressures might be zero. Thus, if one is trying to measure pressure under such circumstances, an error will be caused due to the interfering acceleration input. Similarly, in this case, if the manometer is not aligned properly with the gravity vector, it may cause an output signal X even though no pressure difference exists. Thus, the tilt angle theta is an interfering input. Now, the modifying inputs for the manometer system include ambient temperature and gravitational force. Ambient temperature exhibits its influence in a number of ways. First, the length of the calibrated scale may change with temperature, causing the proportionality factor relating the pressure difference P1 minus P2 to X to be modified whenever the temperature varies from its basic calibration value. Also, the density of the manometric fluid varies with temperature, again leading to a change in the proportionality factor. Similarly, a change in the gravitational force due to changes in location of manometer, such as moving it to another country or putting it aboard a spaceship, leads to a similar modification in the scaling factor. So please note that here the desired inputs P1 and P2 and interfering inputs acceleration and tilt angle theta are modified by the modifying inputs temperature and gravitational force. So while designing an instrument or while measuring, we should implement techniques to reduce or nullify the interfering and modifying inputs. Next, we will learn about performance characteristics. Performance characteristics shows the performance of instruments to be used. These characteristics will give us an idea about how well the instruments measure the desired inputs and how thoroughly they reject the spurious inputs. Also, please note that performance characteristics are also called measurement characteristics. Measurement characteristics. Okay, now the treatment of instrument measurement characteristics has generally been broken down into two sub-areas of static characteristics and dynamic characteristics. Static characteristics are a set of criteria which are used to measure the quantities that are either constant or vary very slowly with time. That is, these characteristics describe the performance of the instruments related to the steady-state input-output variables only. So, static characteristics give us a meaningful description of the quality of measurement without becoming concerned with the dynamic descriptions involving differential equations. On the other hand, many other measurement problems are concerned with rapidly varying quantities. For such cases, the dynamic relations between the input and output must be examined, generally by the use of differential equations. Performance criteria based on these dynamic relations constitute the dynamic characteristics. Now, let's study the static characteristics in detail. We will begin our study of static performance characteristics by considering the meaning of the term static calibration. All the static performance characteristics are obtained in one form or another by the process of static calibration. The calibration of all instruments is important since it gives us the opportunity to check the instrument against a non-standard. Here is a general setup for static calibration. Static calibration refers to a situation where the interfering and modifying inputs are kept at some constant value and the desired input is then varied over some range of constant values, causing the output to vary over some range of constant values. Therefore, by static calibration, the relationship between the output signal and the quantity under study is experimentally determined. Also, please note that it is necessary to repeat the static calibration when the interfering and modifying inputs assume different levels. The process of calibration requires the presence of a standard instrument with which the output signal of the device is to be related. Here, this is the instrument or device to be calibrated. This is the standard instrument and we assume that the reading of this instrument is true value. So we assume that the measurement of this instrument is the true value of measurement. Now we will also see the reading of our instrument under calibration. Also keep in mind that while calibrating, we keep the interfering and modifying inputs at some constant level and those levels are monitored by standard instruments. Now we will compare the readings delivered by the device under test with those of the standard. The output of the comparison can result in three scenarios. First one is no significant difference between the reading of standard and device under test. Secondly, a significant difference is noted but no adjustment is made. And the third scenario is an adjustment is made to reduce the difference in readings to an acceptable level. Strictly speaking, the term calibration means just an act of comparison and does not include any subsequent adjustment. Now, these standards are classified into three ways. They are absolute standards, secondary reference standards, and working standards. Absolute standards are defined via fundamental quantities of measurement like length, mass, and time and does not require calibration. The term absolute signifies the fact that these devices are independent and not relative. In India, the absolute standards, or in other words, primary standards, are kept in national physics laboratories. Next, we have secondary reference standards. These are designed and constructed from absolute standards. In India, these are kept in laboratories set up by NPL at state levels. Then we have working or laboratory standards. Working standards are calibrated in terms of secondary standards and are generally meant for on-the-job or field calibration works. In India, they are maintained by the Department of Weights and Measures of state governments. When a measuring system requires calibration, a proper standard whose accuracy is greater than that of the measuring system should be selected. A rule often followed is that the calibration standard should be at least 10 times more accurate than the system being calibrated. Now, a term you should be knowing is traceability. It is the ability to trace the accuracy of a standard back to its ultimate source in the fundamental standards present at the National Physics Laboratories. Another important topic to discuss is how often we need to calibrate the instruments. But this is a wrong question to ask. The correct question should be, when should we calibrate the instruments? We must always calibrate the instrument before an important measurement. We should also calibrate the instrument at fixed intervals as recommended by the manufacturer. Also, we should calibrate the instruments in intervals set by the regulatory boards. Environmental conditions is another factor. An instrument used in extreme environmental conditions should be calibrated more often than the one used in stable conditions. Next, if an instrument is transported frequently, it should be calibrated. Also, if you drop or otherwise shock an instrument, it is wise to calibrate it afterward. Okay, now that you have an idea about calibration, let's come back to our discussion on static characteristics. The main static characteristics are span, range, accuracy, static error, correction, uncertainty, precision, repeatability, reproducibility, stability, zero stability, resolution, sensitivity, responsiveness, linearity, drift, threshold, and deadband. We will study each of these characteristics in detail. But before discussing these terms, we should know what is meant by true value. True value is the actual value of the property being measured. However, normally an experimenter would never know that the value or quantity being measured by experimental means is the true value of the quantity or not. So in practice, the term true value refers to a value that would be obtained if the quantity under consideration were measured by an exemplar method. By exemplar method, I mean a method agreed upon by experts as being sufficiently accurate for scientific uses or for the purposes to which the data will be ultimately put to use. On the other hand, measured value refers to the value of quantity indicated by the measuring instrument. Okay, now that you have an idea about true value and measured value, let us define each of the static characteristics in detail. First one is range. Range can be defined as the measure of the instrument between the lowest and highest reading it can measure. For example, if a thermometer can measure a maximum temperature of 100 degrees Celsius and a minimum temperature of minus 30 degrees Celsius, then we can say that the range of the instrument is between minus 30 degree to 100 degrees Celsius. That is, the range of the instrument is between minus 30 degree to 100 degrees Celsius. Or in many times, we say that the range of the instrument is simply 100 degrees Celsius. Next term we need to familiarize is span. Span is defined as the algebraic difference between upper and lower range values. For instance, if we take the same example of thermometer, we had a range of minus 30 degree to 100 degrees Celsius. Therefore, the span of the thermometer is 100 degrees Celsius minus minus 30 degrees Celsius, which is 130 degrees Celsius. Okay, in general, if in a measuring instrument, the highest point of calibration is x2 units and the lowest point of calibration is x1 units, then the range of the instrument is x1 to x2 units or simply x2 units, and the span of the instrument is x2 minus x1 units. Next, we will learn about accuracy. Accuracy is defined as the closeness of indicated value to the true value of the quantity being measured. The measured value invariably differs from the true value because of the effects of disturbing inputs such as temperature, humidity, and the performance characteristics of the instrument itself. So, when the accuracy of an instrument is specified, it indicates the maximum likely departure of the indicated value from the true value. The accuracy of an instrument is specified as an uncertainty in the measured value. For instance, if the accuracy of an instrument is stated as plus or minus 1%, it implies that the maximum departure of the reading from true value may account to a maximum amount of plus or minus 1% of the span of the instrument. For example, Consider a thermometer having range 0 to 100 degrees Celsius. Range 0 degrees Celsius to 100 degrees Celsius. So here span is 100 minus 0, which is 100 degrees Celsius. Also consider that the accuracy of the thermometer is plus or minus 1% of the instrument span. So accuracy is mentioned as plus or minus 1% of the instrument span. That is plus or minus 1% of 100 degrees Celsius. Okay, that is plus or minus 1 degree Celsius. Now, suppose you measure the temperature as 70 degrees Celsius. That is, this 70 degrees Celsius is the measurement you made using thermometer. Then it means that the actual temperature lies between 70 degrees Celsius minus 1% of span, that is 1% of 100 degrees Celsius, that is 1, and 70 plus 1% of 100 degrees Celsius, that is 1 degree. So that is 69 degrees Celsius and 71 degrees Celsius. So this is the range in which actual temperature will lie. So we usually specify the measurement also considering the accuracy, that is 70 degrees Celsius plus or minus 1% of span. This is how we specify the measurement. Usually the accuracy can be specified in three ways. The first way is just like we discussed, that is as a percentage of span, and we will write the measured value as measured value plus or minus percentage of the instrument span. In some textbooks, this way is also written as accuracy as a percentage of scale range. Okay. Now another way to specify accuracy is accuracy as a percentage of true value. Here the reading is expressed as measured value plus or minus percentage of measured value. In some textbooks, this is also specified as accuracy as a percentage of reading. Next, we have point accuracy. Here, the reading is expressed as measured value plus or minus uncertainty of measured value in units. Also, in this case, no information about the accuracy of other points can be obtained. Let us now see a question so that we get a clear idea about these three ways of specifying accuracy. Suppose we have a voltmeter with range 0 to 20 volt and one of the measurement was specified as 10 plus or minus 0.2 volt. So one of the readings is 10 plus or minus 0.2 volt. This way of expressing accuracy is called point accuracy. We can also express this accuracy as a percentage of full scale deflection or full scale range. So let us do that as a percentage of full scale deflection. Here we know that the instrument range is 0 to 20 volt. Therefore, span of the instrument is 20 minus 0, which is 20 volt. So the measurement can be expressed as 10 plus or minus 0.2 by 20 into 100, which is 10 plus or minus 1% volt. So here the accuracy is expressed as a percentage of instrument span. Now, accuracy can also be expressed as a percentage of true value, that is, as a percentage of true value, or in other words, as a percentage of measured value. So we have 10 plus or minus 0.2 by 10 because 10 is the measured value into 100 volt, which is 10 plus or minus 2% volt. So here the accuracy is expressed as a percentage of true value. Now one thing to keep in mind is that Accuracy mentioned in terms of scale range is constant for the whole range of instrument, while accuracy mentioned in terms of true value changes depending on the true value. To make the concept clear, let us again consider our 0 to 20 volt voltmeter. Let's say in one case the manufacturer mentioned the accuracy as plus or minus 1% of the FSD, and in the other case the manufacturer mentioned the accuracy as plus or minus 1% of the true value. Let us also consider the same set of readings in both cases and see the accuracy of each reading in both cases. Let's say the readings are 1 volt, 5 volt, 10 volt, 15 volt and 20 volt. In the case of accuracy mentioned as a percentage of FSD, the reading of 1 volt can be written as 1 plus or minus 1 percentage of 20 volt, because 20 volt is the span of the instrument, which is 1 plus or minus 0.2 volt. Similarly, 5 volt can be written as 5 plus or minus 1 percentage of 20 volt, which is 5 plus or minus 0.2 volt, and similarly 10 plus or minus 1 percentage of 20 volt, which is 10 plus or minus 0.2 volt, and we have 15 plus or minus 0.2 volt and 20 plus or minus 0.2 volt. Now we will see the case where accuracy is mentioned as a percentage of true value. Here the readings can be written as 1 plus or minus 1 percentage of 1 volt, because 1 volt is the reading, which is 1 plus or minus 0.01 volt. Similarly, for 5 volt we have 5 plus or minus 1 percentage of 5 volt, which is 5 plus or minus 0.05 volt. Similarly, for 10 volts we have 10 plus or minus 1 percentage of 10 volt, which is 10 plus or minus 0.1 volt. Similarly, for 15 volts, 15 plus or minus 1 percentage of 15 volts, which is 15 plus or minus 0.15 volt. And for 20 volt we have 20 plus or minus 0.2 volt. So you can see that when the accuracy was mentioned in terms of scale range, this plus or minus 0.2 volt was constant throughout. That is, you can see all these values are plus or minus 0.2 volt only. However, when the accuracy was mentioned in terms of true value, the accuracy dependent on the true value. See, all these values are different and dependent on the true values. Okay, now the next static characteristic we need to learn is precision. Precision is defined as the capability of an instrument to show the same reading when used each time. Theoretically, if an input quantity of the same value is applied repeatedly to the instrument, then the indicated value is expected to be the same under exactly the same environmental conditions. But in practice, the readings will be clustered around a value in a random manner. The more number of readings fall very close to the value, the more precise the instrument is. Now, let's take a practical example to understand the distinction between accuracy and precision. Consider a shooter aiming at the target shown here. The objective of the shooter is to hit the center. Let's see 4 scenarios of the shooter. The red dot shows the points where the shots are hit. Now in the first case, that is this case, the shots are close to the center. Therefore, they are accurate. However, the shooter is unable to hit the same point again. That is, all his shots are scattered. That means he is not consistent with his shots. Hence, not precise. Now let's take the second case. Here, the shots are not close to the target at center. Therefore, not accurate. However, the shooter was able to be consistent with his shots, that is, all his shots are close to each other. Hence, he is precise. Now, in the next case, as you can see, the shooter is neither precise nor accurate. Therefore, not accurate and not precise. And in the last case, all the shots are close to the center, therefore accurate, and also all the shots are close to each other, that is they are consistent, hence precise. So I hope you get a general idea about accuracy and precision from this example. Now let's see another example which is more relatable for science and engineering students. Let's say 4 students performed an experiment to measure the voltage across a resistor. Say the actual value of voltage is 4.3 volt, and these are the measurements made by each of the 4 students A, B, C and D. Let us now rate the accuracy and precision of data presented by each student. In the first case, that is in student A's case, all the readings are clustered around 4.5 volts, but the actual value of voltage is 4.3 volt. So the readings are not very close to the actual value. Therefore, this is not accurate. Now let's see the case of student B. Here also the readings are not very close to the actual value of 4.3 volt. So this is also not accurate. Now taking the case of student C, the readings are pretty much close to the actual value, right? The 4.25, we have 4.3, then 4.321, again close to 4.3, and 4.295 is very close to 4.3, and 4.342 is also close to 4.3. So we can say this data is accurate. In the case of student D, all the values 4.301, 4.299, 4.302, 4.298 and all are very close to 4.3 volt. So this is also accurate. Let us now check the precision of these data. Let's see, in student A's case, do the values agree with each other? All of these values are around 4.5. That is, they are very close to each other. So student A's data is precise. Now let's see the case of student B. Here the data is not precise because the values 4.016, 4.137, 4.541 and 5.104, these values are not very close to each other. That is, they do not agree with each other. So the data is not precise. Similarly, for student C also, the data is not very precise. So not precise. Now student D's data is very precise. 4.301, 4.299 are very close to each other. Also, they are very close to the values 4.302 and 4.298. I mean, here the difference between values are of the order 0.001 or 0.002. That is very close. So, this data is very precise. In general, lower the difference between values of the data, the more precise the data is. So to conclude, we need any instrument to be highly accurate and highly precise. That is, we need instruments that are highly accurate and highly precise. Okay. Now, due to time limitations, we will end our lecture here. We will continue our discussion on static characteristics in the next video. To summarize the lecture, we learned about a generalized input-output configuration for instrument systems. Then we learned about performance characteristics and learned that it can be divided into static and dynamic characteristics. Then we studied about static calibration and continued our discussion on static characteristics in detail. If you have any doubts, feel free to ask them in the comments. I will try to answer them with the best of my knowledge, or some other viewer can also help you. Also, if you found the lecture useful, please like the video and support us by subscribing to the channel. In the next video, we will discuss more on static characteristics. Thanks for watching and have a nice day.